This project started about 4.5 billion years ago, when a cloud of dust and debris coalesced in the empty void of space to form a ball of rock. Soon after this, and then, in a time that would come to be known as Monday, May 16th, 1960, some dude in California made the world's first working laser. Using synthetic ruby and a helical flash tube, the aftershocks of those coherent photons reverberate even today. 54 years later, a guy named Ben built his own ruby laser and posted a video about it on a website called YouTube. And 4 years after that, the video was seen by me. And, well, here we are. Ever since I saw Applied Science's video, I knew I had to build a solid-state laser of my own. And I mean, come on, it's like lasers, man. Who with even a glimmer of light in their heart doesn't get excited about lasers? Now, it's taken me a few years to get everything in order, but I'm at the point now that I can actually start putting the pieces of the puzzle together. But at the risk of being some kind of photonic poser, I decided to pursue something a little off the beaten path. Rather than a ruby laser, I'm trying my hand at neodymium-doped silicate glass. Or just ND glass, if the two of you know each other. Now, full disclosure, this thing does not currently work. Or if it does work, I don't have equipment sensitive enough to prove that. I think it's close, but as we'll get into, it still needs some fine-tuning. So this video is going to be a look into the engineering decisions that have gone into the project so far, what is currently working, what I think is not currently working, and the next steps I plan on taking. With any luck, this will end up being a 2-part series, and in the next video I can show off a working laser. To start, let's look at a high-level schematic of all the major parts of a generic solid-state laser. Then we'll talk in detail about each part in the context of the specific laser being built here. At the high level, a solid-state laser looks like this, and the whole thing works on the principle of energy transfer and conversion. First, energy is converted from stored electrons into photons in the form of a flash of light from a flash tube. The network of components responsible for forming this pulse of light has been given a clever name, the PFN, or Pulse Forming Network if you're not much into the whole brevity thing. The photons produced by the flash lamp are absorbed by the laser medium, which I'm going to call the laser rod because it's shaped like a rod, and then are re-emitted as other, differenter photons. The laser rod and flash lamp are contained in an enclosure to ensure that the maximum amount of light makes it to the rod. The more differenter photons then spend the rest of their short lives bouncing between two mirrors. They leave one end of the rod, hit this mirror, bounce back through the rod and hit the other mirror, only to be bounced back through the rod again. On its own, this bouncing light between two mirrors does not a laser make, but the rod has another trick up its sleeve. Thanks to some quantum mechanical screwiness, each time a photon passes back through the rod, it is more likely that another photon of the same wavelength and traveling in the same direction will also be emitted. Given enough passes through the rod, any photons that are not traveling normal to the mirrors or are of the wrong wavelength will die out, while the ones that are of the right wavelength and are moving in the right direction will be amplified. So that in the end what we are left with is a coherent group of photons with the same wavelength moving in the same direction, trapped between the two mirrors. And because of that whole wave-particle duality thing, you can either think of this system as particles bouncing between two mirrors, picking up friends with each trip through the rod, or as a standing wave between the mirrors, like the waves that would exist in a vibrating string or a bottle. This is in fact where the key properties of lasers come from, the things that separate them from other light sources. They produce light of a single wavelength, and that light travels in a very directional beam. The standing wave between the mirrors selects for both parameters. Now, the light would be more than happy to just be left alone between the mirrors until internal loss is converted into heat, but because us humans seem to be obsessed with this idea of purpose, we figured out that if you make one of the mirrors only partially reflective, we can extract a beam of this coherent light and use it for scanning barcodes, finding gravitational waves, entertaining cats, the useful laser stuff. Starting with the laser medium is a good choice, because without this, the whole thing just becomes a mediocre camera flash. As mentioned before, I went with the somewhat less common medium ND glass. This is related to the more common ND YAG. The differences are somewhat not important in the context of this build, but they are interesting, so just for a bit of fun, let's dive in a few feet. The YAG in ND YAG stands for yttrium aluminum garnet, essentially the same thing as the gemstone just grown in a lab. The ND in ND YAG indicates that some small percentage of the yttrium atoms have been replaced with neodymium ions, in a process known as doping. ND glass is similar, but it doesn't have to conform to the limiting crystal forming rules of the square world, and has ascended to a higher plane of existence, the land of amorphous solids. This free-flowing form of solid-state being makes ND glass popular in the lab, but not so much at parties. Composed of silicon and oxygen, with some small percentage of the silicon replaced with the same neodymium ions as before, glass is used over YAG because you don't have to deal with the persnickety process of growing large synthetic crystals, and much larger rods can be created when compared to ND YAG. Also, they can be doped to much higher concentrations, have broader absorption bands, and, of chief importance to us weekend warriors, cost significantly less than ND YAG rods. We are still mostly confined to surplus, with eBay being the prime getting spot, but you can get your hands on much larger rods for much lower prices when compared to YAG. This is the rod that I ended up getting. It was an eBay purchase, and it used to be a larger rod that was damaged but refinished, supposedly by a professional optics shop. This is a rather obscure Soviet-era Russian glass called GLS-1. There's not a whole lot of information available about it online. The best I can find is this table in the riveting text, Handbook of Solid-State Lasers, Materials, Systems, and Applications, that puts the dopant concentration at 2.5% by weight. Other than that, I can't find too much about it. The rod looks to be in good condition, the faces seem well ground and polished, but the most important aspect of these rods is that the faces are super parallel to each other. I have no cert for this rod verifying this, nor do I have any way to test how parallel they are myself. So on this aspect, I'm left to trust the seller, that whoever finished this rod did their job right. The outside of the rod has some damage, but that's a feature I added myself. We'll get into what happened there in a bit. So now that we have a laser rod, we need a way to excite the neodymium ions into a higher energy state. In this case, we are going to use a high energy flash lamp. The ions absorb photons with a wavelength of 808 nanometers, and it just so happens that xenon gas, when excited with an arc, produces a spectrum of light with a peak at 808. How serendipitous. The flash tubes used to pump lasers are similar to the ones used in ordinary camera flashes, just beefed way up. To start, they are typically made of quartz glass rather than bog-standard soda lime. This makes them much stronger and able to withstand the much higher internal forces produced when operated at the energies needed to pump lasers. The downside to this construction is the quartz glass passes some ionizing UV radiation that soda lime blocks. Though some do use special quartz glass that blocks it, so just keep that in mind. The gold standard for these types of flash tubes used to be the Perkin-Elmer's EG and G series, but I can't seem to find them much on eBay these days. So the lamps I ended up with are maybe more of a red standard than gold. These are the IFP-800 and the INP-3-7/80A, also Soviet-era Russian-made tubes. These things are available all over eBay and other sources for pretty cheap, which is why I was initially drawn to them. These have a bore diameter of 7mm and an arc length of 80mm, which matches the dimensions of the rod pretty well. The INP tube also has a dichroic coating on the outside of the glass to cut the UV end of the spectrum. Now they do flash, but as we'll get into more in a second, I think these flash tubes might be the root of my laser woes. When designing for high-power xenon flash tubes like this, the number that you live and die by is the explosion energy. This is the amount of energy that would cause the tube to catastrophically fail in a single flash. You can approximate the explosion energy with this equation, and for the lamps I have here, it should be about 2,000 joules, for a pulse time of 750 microseconds. So if I flashed this tube with 2,000 joules in 750 microseconds, it would explode. Now it's been my experience that these things work better when they're in one piece, so we want to run them at some fraction of this explosion energy. And the number of flashes you can expect out of a tube is given by this equation. The sweet spot is in the range of 10 to the 4 to 10 to the 6 flashes, which corresponds to about 0.3 times the explosion energy. So in this case, we'll call it about 600 joules. Okay, so 600 joules. What now? Well, to explain that, we need to talk about the next piece of the laser puzzle, the pulse forming network. The job of the PFN is twofold. It stores the energy needed for the flash tube, and it controls when that energy is released. The energy is stored in a capacitor, in my design actually a bank of these large film caps. These are 750 volt, 290 microfarad caps from Unelytic, another eBay find. I have them wired in parallel to get a total of 1,160 microfarads of capacitance at 750 volts maximum, and I'm charging them from an electrophoresis power supply. This one is the EPS 600 from Pharmacia Biotech, and it can output a maximum of 600 volts. A brief word about these electrophoresis power supplies. They are a convenient way to get reasonably safe and controlled access to high voltages in the home shop. You can even set current limits on most models, but they can be a little finicky to get to work. They often don't want to start unless they have a load attached, and can also get a little wigged out when connected to a large capacitor where the current draw changes as it charges. This one in particular won't even get to the full 600 volts, it gives an error about a sudden load change before it gets there. And I have had problems with it not even starting and complaining about ground leakage current. This was fixed with the classic wrap the ground lug in tape trick, so if you have one of these and are getting that problem, this might be the solution. Just remember to bury the cord before the insurance man gets there when the house burns down. The other issue with these things is that even surplus, they are pretty expensive, and often have little to no documentation. So you're kind of shooting blind with results to if the one you get is going to work for charging capacitors. All that is to say, in my opinion, electrophoresis power supplies are not the best option when it comes to charging high voltage caps in the home shop. A much better option is a neon sign transformer and a diode rectifier. Even a modestly sized NST and a single high voltage diode will work and cost a fraction of an electrophoresis supply. To be sure, they are not as safe, and there are some other things to consider. But we'll get into NSTs in the next video. For now, the caps are charged with this supply. Alright, no, even my tangents have got tangents. What was I even talking about? The PFN. So if we charge the bank to 600 volts, we now have about 200 joules at our disposal. If we then connect the bank across the flash tube, nothing will happen. This is because the 600 volts in the caps is not enough to break down the xenon and strike an arc across the electrodes in the tube. The distance between them is just too large. To get a flash, we need to trigger the tube. And while you could try telling it offensive jokes, a much more efficient scheme has been developed. Essentially what we need to do is send a high voltage pulse to the lamp to start a low resistance path between the electrodes. Then the caps can dump their energy and the tube will flash. This pulse needs to be really high voltage, like tens of kilovolts high. For this lamp, I use a 30 kV pulse, and that seems to be the minimum to get it to fire reliably. To get this pulse, I use this monstrosity, and trust me, it's just as bad as it looks. This box of a death trap charges this small electrolytic cap to about 300 volts, then using a beefy SCR dumps it across the primary of this auto ignition coil, which is basically just an oil-filled transformer, about 80 to 1 turns ratio. So we get 25 kV out on the other end. That is then transferred through this high voltage connector through a piece of 30 kV rated cable to a thin piece of magnet wire wrapped around the outside of the tube. The ground of the transformer is connected to the ground of the cap bank. The high voltage pulse couples through the glass of the tube and creates a small streamer that connects the two electrodes of the flash tube, and you get one flash. Then you have to charge up all the capacitors again to get another one. I put the trigger circuit in this little box with a voltmeter on the cap, a button to trigger the SCR, and a little key switch for, style points. Okay, so now we have a tube that flashes and a rod to flash. But if we just put the two of them next to each other, most of the photons from the tube are going to be wasted. So we need to come up with some kind of enclosure to both contain the whole package and make it easier to deal with, but also to get the maximum energy transfer to the rod. If we imagine the rod and the lamp next to each other viewed from the end like this, the shape of the enclosure needs to be such that no matter which direction a photon leaves the lamp, it makes it to the rod. If we assume that whatever it's made of is reflective to light, we need the set of all points so that the angle of incidence equals the angle of reflection. Aha! We have stumbled upon an ellipse, with the rod at one focal point and the lamp at the other. How serendipitous. Now, while in theory any ellipse would accomplish this, there is room for optimization. As explained in what many consider to be the Bible of solid-state reference material, Solid-State Lasers, a Graduate Text, the eccentricity of the optimal ellipse depends on the ratio of the diameters of the rod and the lamp. The results are presented in this graph, but for you masochists who are into that kind of thing, there is also a rigorous geometric proof. In this case, the ratio of rod diameter to lamp diameter is about 1.13, so I need a chamber with an eccentricity of 0.3 for maximum transfer. Okay, so I'm editing this now, and I went off about this whole eccentricity thing, but never actually explained what it means, so let's do that now. If we look at the ellipse from before, we can call the distance from the center to one of the foci C, and the distance from the center to the edge A. Then the eccentricity of the ellipse is given by E is equal to C over A. And this describes basically how squishy the ellipse is. The closer to 1, the more stretched out the ellipse. You can think of a circle as an ellipse with an eccentricity of 0. And on the other end of the spectrum would be a line, which is like an infinitely squished ellipse and has an eccentricity of 1. So the ellipse we need, with an eccentricity of 0.3, is like a circle that's just been barely squished out. Okay, that's what eccentricity is. Back to our regularly scheduled program. So over in CAD, we can start messing around with some different configurations. And this is the one that I came up with. It really came down to balancing the size of the chamber and keeping the eccentricity as close to 0.3 as I could. A larger rod to lamp ratio would have given me more freedom in this design, so keep that in mind. I planned on getting it machined out of aluminum and then polishing the inside myself. Aluminum is not the most optimal material, as its reflectivity graph dips right at the critical absorption wavelength for the rod. Gold or copper would be a better choice, and while a 10-pound solid gold laser cavity probably could be turned into a pretty clever tax dodge, I decided to accept the loss and just go with aluminum. I did the polishing by wet sanding up to 3000 grit, then doing the final polish with Mother's mag and aluminum polish and a microfiber cloth. Now I have no affiliation with this company, but I must say it does an excellent job of polishing aluminum, like it leaves a proper mirror finish. So if you ever need to polish aluminum, this is the stuff. Once again, no affiliation, but hey, call me. After it's been polished, we can see the ellipse working its magic. The pen looks like it's actually inside the lamp when I put it at the other focus point. In addition to this chamber, I also designed 2 end caps to hold the rod and lamp. They just bolt into the end of the chamber and also hold the 2 halves of the chamber together. And I also designed a plate to mount the chamber and hold the mirror mounts, which is the perfect segue to talk about the mirrors. As mentioned before, 2 different kinds of mirrors are needed to make a working laser. One that reflects 100% of the light that hits it, called the full reflect or FR, and one that reflects only a fraction of the light and lets the rest of it through, called the output coupler or OC. The gold standard for lasers operating in the frequency of this one are dichroic mirrors. These are basically just very flat pieces of glass with a thin film of metal deposited on one side. The mirrors I have here are from a Chinese company called Master Laser. I'm not sure if they still sell these mirrors as I bought them several years ago, but it was nice to be able to access new stock mirrors at a reasonable price. Places like Thor Labs or Edmund Optics will sell to individuals, but the prices are going to be pretty ridiculous. On the other hand, you would be sure you're getting something of quality, so keep that in mind. Other than that, eBay is once again going to be the place to look for mirrors, though finding a matching set might prove to be difficult. In any case, I have 2 FR mirrors and 2 OCs, one that lets 40% of the light through and one that lets 80% of the light through. Solid-state lasers like this are very high gain and need very little of the light to be reflected back in order to laze, so this 80% transmission OC is not crazy. Because the two mirrors need to be made very parallel to each other, they must be placed in some kind of adjustable mount. The really nice ones have veneer scale micrometers on the adjusts and other features, but for the home shop budget, this more common style of mirror mount should suffice. I also got these from Master Laser, but they are available elsewhere. I think they are made for like CO2 laser cutters, so look around at hobby CNC places. So how are the mirrors aligned? The easiest way is to use another laser. A high-quality helium neon laser is best, as it will have a very well-collimated beam. In theory, if you place a card with a hole over the output of this alignment laser and shoot it down the two mirrors, when the mirrors are in perfect alignment, the beam will go right back into the laser and you will have an interference pattern on the card. I have not gotten this to work, or at least I don't think I have. I can get all the dots to line up and disappear into a single point, but I have yet to see the interference rings that I was expecting. This might have something to do with the fact that these mirrors are really no different than pieces of glass to the wavelengths of visible light, but I'm really not sure. I think I have them aligned well enough, however. Don't bother trying to align with the rod in place, you'll never get anywhere. It adds too many additional variables. If the ends of your rod are ground flat and parallel to each other, the alignment of the rod itself is really not that critical. The alignment of the two mirrors is much more so. So align the mirrors first and then add the rod. Okay, so we have a laser rod and a flash lamp in a properly designed and reflective chamber, a cap bank and a trigger circuit powering the flash lamp, and the whole thing is between two supposedly properly aligned mirrors. Now let's go over some of the problems I'm currently having with this thing and what my next steps are to try to fix it. First, these flash lamps. They are long, like comically long. They're almost 3 times as long as the actual arc lamp. And this caused 2 problems. One, I had to make the whole laser longer than I would have liked to, in order to get the mirror mounts out of the way of the lamp. Not the end of the world, but it would have been nice to make it smaller. Another issue this caused is the ends of the lamp are very close to the mirror mounts. This caused the trigger pulse to find a better path to ground through the insulation of the magnet wire and then through the mirror mount, instead of going through the xenon like it's supposed to. I tried insulating the ends of the lamp, first with hot glue, then with some custom printed connectors, to no avail. At voltages this high, the intuition you have for how much insulation is enough really breaks down. After fighting with this for a few weeks, I finally just turned the mirror mounts around so they're further away from the ends of the lamp. This mostly solved the issue, though sometimes it still does arc. The issue now is that I have to set up the mirrors backwards to the way they should be set up, and the adjustment screws are in a really awkward place, which makes alignment a real pain. The next problem has to do with the capacitors I have powering the tube. For lasers like this, you need a short pulse time, on the order of 700 microseconds. And that's pretty fast. In order to get a pulse that fast, you need to have a small overall capacitance. But in order to get the energy needed, you need a high voltage. I went kind of the opposite route. I have a fairly large capacitance and a pretty modest 600 volts. This decision was mostly based on the fact that 600 volts was the best electrophoresis PSU I could find at the time. What would have been more optimal is to put my 4 caps in series and end up with like 70 microfarads at a maximum of 3000 volts. This would not only give me a shorter pulse time, but also a higher maximum energy, 324 joules rather than the 200 joules I have now. In fact, I've already built a new high voltage power supply that goes up to 3000 volts. Definitely needs some tweaking, but we should see it in the next video. It was actually when doing some tests with this new supply that I had my first real accident of this project. I had the caps wired to the tube and the trigger circuit was set up and ready to go. Just as I got to 3000 volts, the flash tube violently exploded. Thankfully, it was inside the housing and I was wearing safety glasses, but it still gave me quite the heart attack. As far as I can tell, no serious damage was done, other than to the lamp. The rod has a few nicks on the outside, but that shouldn't be an issue as long as the ends are still undamaged, which they appear to be. The chamber sustained no damage as far as I can tell. What I think happened here is that I got the voltage across the tube into the kilovolt range, and it was able to arc across this conductive dichroic coating and sort of self-trigger. Now I have no idea why the rod exploded. I should have been well under the calculated explosion energy, but it was really the final straw with these tubes. I've been fighting this conductive coating from day one, they're poorly designed, I've had a few crack and the seals break. I guess I shouldn't be too surprised that 40-year-old command economy produced flash tubes are not of the highest quality, but getting a new tube is the first step I'm going to take towards getting this thing working. And yes, before anyone asks, I did try calling the manufacturer, but their number was disconnected sometime back in '91, so no luck there. With any luck, I can snag something domestic and at least made within the last decade. The last issue I think I'm having has to do with how I was testing the laser. I was just putting a piece of thermal receipt paper in front of the OC and hoping to see some evidence of lasing being burned into it. So it's possible that I was getting coherent photons, but I just didn't have sensitive enough testing methods. To address this, I have acquired some professional Zap-It paper. This is some pretty cool stuff. It's not thermal paper like the other stuff I was using, it's a little more subtle than that. And I should be able to actually see the transverse mode, something we'll get into in the next laser video, on the sheet. I got the low power version, so hopefully if I'm getting some lasing, I should now be able to see it. So that's my attack plan moving forward. A new, higher quality, and hopefully shorter flash tube, higher energy with lower capacitance, mirror mounts turned around the right way, and some more legit kit to test the output. When I get evidence of lasing, I can start to mess around with maximizing the output power and things like that. But hey, one step at a time. So that's the end of part 1 of the laser build. I hope I was able to condense what is a pretty complex topic into a somewhat enjoyable half hour. If you have questions, suggestions, things I might have missed or glossed over, leave them in the comments. I'll address them as best I can in the next video, where with any luck I can show off a working laser. That's all I've got for now. As always, take it easy.